Hi, now that we discussed the other part of the GLM, that is the general case of link function. So here, our notation is mu is equal to the expectation of y. And assume that a linear predictor, so the generalized linear model, that is still a kind of modification of a linear model. So the eta is equal to linear combination of x1 to xp and the intercept. So we can write this as the beta transpose x. And here, the eta that should be equal to the g of mu. So mu is the parameter which express the expectation of y. And or we can say that the mu is equal to the g inverse of eta. So this is maybe a little more intuitive because we define eta is equal to beta transpose x. So what's the link between mu and eta? So if we use the g inverse, then eta becomes mu. In logistic regression, the g mu is equal to logit function. So this is basically the probability to the odds ratio. And the g inverse of eta, so this is I logit of eta. So this is the linear predictor to probability. So this range is from 0 to 1. So this range is from all real numbers. Yeah. And okay, so now that we have the g inverse of eta is equal to mu, so what is y? So y is equal to g inverse of eta. So this is expectation of y and plus epsilon, that is an error term. So this is the structure of the generalized linear model. And this is different from linear regression with transformed response. So if we transform y by function, so this we use g, but just any function, maybe we say h. H of y is equal to eta plus epsilon. Eta is just a linear combination of predictors. So that is often used in practice, but this is slightly different. You can see g of y is equal to eta plus epsilon. So epsilon is actually a kind of included in g. So if you map all both sides by g inverse, y is equal to g inverse of eta plus epsilon, and the epsilon is included in the g inverse. So it's a little different from generalized linear model. So now we think about a good link function for each problem. So we define the canonical link. So we have defined theta. So originally, the distribution have some parameters. For example, binomial distribution have two parameters, n and p. But we defined theta using exponential family. So in the exponential family, the density should be exponential of y times theta minus b of theta over a phi, and so on. So we defined theta. And actually, if this theta is represented as the linear combination of predictors, that is eta, then we say G is a canonical link. And usually this is the best choice. So that means the procedure to fit generalized linear model is, okay, so we think about the exponential family first. Then what is theta? We identify. So theta is sometimes, okay, log of mu over 1 minus mu, or log of mu, depending on the distribution. Then we use that link function. And we assume that this theta is equal to linear combination of the intercept and x1 to xp. So this link is called canonical link. So once you identified the relationship between original parameter and the parameter theta in the exponential family, it's automatically, canonical link is automatically determined. Okay, so examples. So first, normal distribution. It's a little bit trivial case. So mu is equal to theta, as we have seen. So the canonical link is G mu is equal to mu. The second example, the binomial distribution. And we have identified the log of p over 1 minus p is equal to theta. And also we know that the mu, expectation of y, is equal to np. So the canonical link, there should be the link between theta and mu. So that means the mu is equal to np, so p is equal to n over mu. So g of mu is equal to mu over n over 1 minus mu over n. I think that in most textbooks, it was mentioned that the link is mu over 1 minus mu. So probably they only think about just the binary case. And that makes the argument easier. But if we follow the notation of the textbook, I believe that the g of mu is the mu over n over 1 minus mu over n. And some other link, the Poisson distribution, the canonical link is eta is equal to log of mu. And the gamma distribution is this distribution. Then eta is equal to the mu inverse. So gamma distribution, the range is the okay, so the random variable, the range is from 0 to infinity. So we need some transformation, and actually the eta is equal to the mu inverse. And the inverse Gaussian distribution, this is basically related to the time that the normal process, I mean the Brownian motion, reached certain level, so that the random variable which represents the time to achieve the certain level for the Brownian motion. So that one, the link is eta is equal to the mu inverse. So, so this is the general theory of the link function. So we can define any link function, but usually the canonical link is the best choice.